This is closely related to SDK, some aspect designs, and AI. This is because the AI's context window is limited. So if you allow AI to freely handle any of your requests, you'll find that its approach to the same task can be very different and quite scattered. Then you'll have a dozen services in your project. If you try to manage and sort them out, you'll find it impossible and it will be extremely painful. So in the era of AI, your ability to design architecture becomes very important. Architecture design involves SDKs, modules, and standards at various system levels. And at the same time,
AI,
if you have a good infrastructure, AI only needs to understand your architecture since the context window is limited. There's much less it needs to understand, so it can efficiently handle your requirements based on your architecture. And I've even found it can give feedback to further optimize your architecture. This creates a positive cycle, making your projects increasingly manageable. Aside from structure, which is important for AI, I believe relationships are even more crucial. For example, regarding logs, my log design isn't based on strings. Everything is standardized. My logs are all encapsulated using an event-based approach. All messages are included, followed by user IDs and related parameter injection. So why do I encapsulate all messages as events? It's because when AI traces, it uses relationships to associate things. It will see, okay, in your order service, there are these logs and events, and it can work through these relationships. It can quickly grasp the entire event relationship within the order service, helping it better understand your business processes. This relationship is crucial. Without it, sometimes it lacks the connection to find certain minor details in the process, and it can't overcome those hurdles. It's the same with metrics. All my metrics are also encapsulated this way, so the system can identify all the critical points across the platform. Sometimes, after designing the architecture, I just mention a requirement, and it has already addressed all the system's critical points. And for example, with logs, if you modify one part, the change can propagate through the logs. And the system will automatically know that if you alter one part of a process, related areas also need updating. It understands this through the relationships. Besides structure, establishing these relationships is a crucial part of architecture design. Another aspect impacting AI is that you can see my services actually have very little configuration and code. Let's say, for instance, with the order service, the configuration for my order service is minimal, but it uses many frameworks. Almost all of these frameworks are actually used. This is because I've unified all configurations here, encapsulating and managing them. All configurations are encapsulated here. Everyone can share it, and each service can use this configuration. If needed, each service can declare the same configuration to override it. What are the advantages of this? The benefit is that sometimes your configuration affects how your implementation logic should be executed. If you have to let AI handle each service request, it would need to understand all your framework configurations anew each time. When you switch to another service, it also needs to understand everything again. This context switching can be very frequent. With my approach, I simply enforce AI within its agent guidelines to adhere to my specifications. This context remains fixed and never needs switching. You can save a lot of your tokens, and the AI's mastery of your system will become more proficient eventually. It will proactively suggest recommendations and optimizations, which is very helpful. Here's another small example, but it has a significant impact on AI. I'll use the controller and Kafka consumer as examples. Let's first look at the position controller. Can everyone see if there's anything special about this structure? Yes, its interface, its connection is made using a single interface. Its interface is declared here in the interface section. What's special about this? I'm looking for the upstream caller for this interface. Let's take a look. Okay, the upstream caller. You can find that the upstream caller usually redundantly declares the same interface. But here, I don't need to do that. I just need to extend this. With this interface, it automatically inherits these elements. So originally, you would need to declare identical interfaces in two places, one for the client and another for the server. But now you only need to declare it once, and it applies to both places. Besides being easier to maintain, as you only need to modify one place, what are its advantages? Its advantage is that when the client references this interface, it automatically incorporates the models of the input parameters and some validation logic, so you only need to write the validation once, and it can be applied to both the client and server. When someone on the client side needs to use your interface, they can directly use this model and validation, making it much more convenient. When the client wants to invoke your interface, they don't need to communicate with you or maintain documentation. They just directly load this, look at the interface, and see the validation parameters in the model of the input parameters. They will know exactly how to structure the request parameters. This saves a lot of communication time and documentation time. What's the benefit for AI? It means that once these SDK clients import them, all these things become available. AI can directly use these models and validation rules. It doesn't need to declare the same models and validation rules twice across services, saving a lot of effort. Another aspect that helps AI is interface governance. Because the fewer interfaces there are, the easier it is for AI to understand the specific capabilities of your entire service. This small point is about permission control. Most of the time, I've seen many companies in the past where their approach is to use the same interface, like querying positions, and they might open one interface for users. Then they open another interface for internal service calls, resulting in two interfaces. But my approach is to use annotations, allowing the same interface to support two scenarios. I use annotations to handle the respective validation methods, reducing the number of interfaces from 2 to 1, saving a lot. This is helpful when AI needs to scan all your interfaces to understand your business processes. I think it's very helpful as it streamlines the number of interfaces. Now, looking at the Kafka consumer part, it's the same. For the Kafka consumer, the first design I made is that all topics are related. When you reference this topic, you can know which event you need to use to handle and receive the message content. Similarly, this object also has built-in validation parameters. That means when I develop a service, all the validation rules I create can be directly used by the client. This is very helpful. Another part regarding consumers is that many people might implement retries or dead letter queue logic, which can be resolved at the framework design level without requiring AI to handle each interface separately. If AI has to process many service consumers, and each one is implemented separately with slight differences, it can become a burden for AI. you end up using its resources, which impacts its overall effectiveness. Well, let me explain in the context of a distributed transaction scenario. Assuming our distributed transaction involves any solution related to LUCHY, no matter which type of distributed transaction you use, the code for state management will become very complex. So I have created an encapsulation here. Suppose I have a business logic like this. I first write something in the order service. Then I need to send a request to the warehouse service and write something there. After returning, if successful, my service will write something more as part of this logic. Previously, the code might require writing a lot, like what to change if successful or if it fails, and doing many things. But here I have encapsulated it in a service, so you just need to follow your original business logic. Just treat this method as its parameter, and you don't have to worry about state management. Just pass it as a parameter and write your original logic inside. Originally, you just query and write some data to the warehouse, and after finishing in the warehouse, write something in the order service. You just write your original logic here and then hand this over. Pass it to this LUCHY as a service, and all the complex state management of success and failure, what to do upon success or failure, can be ignored. With this, when AI handles all distributed transactions, it will use my solution and apply the same method. It doesn't need to divert attention to state management, saving a lot of effort and resources. Meanwhile, after you extract this method, on the other side, since using LUCHY requires scheduling, your scheduling part is the same. When scheduling, call this method again and use li_when task as the parameter. That's it. Well, that's basically it. You can take a look at this. This is the order service. This is my service. You can also take a look at the try method. It's like with this LUCHY task service, as long as you design LUCHY distributed transactions, everything becomes much simpler. Next, regarding Redis, some parts also need encapsulation to make AI's handling of caching less cumbersome. First, let's talk about reading from the cache. Reading cache involves the same template code, and it always requires handling cache penetration. The protections against penetration are all the same, so after templating it, the parameters passed are the key and TTL, along with the database query method. This way, AI knows that whenever you use the cache, you don't need to write these parts. It directly calls this. Then it handles everything automatically. How to read the database is passed in, and that's it. And here, regarding the cache, the protection mechanisms are automatically handled, including TTL jitter. Besides reading cache, there's a scenario related to batch writing and reading in the cluster, because in the cluster, in the practical group, for batch writing and reading, you need to calculate for each object which batches should be written to which node. That calculation is quite troublesome, but I have encapsulated it here. Whether it's batch writing or reading, AI can directly call this method. Just directly call these methods. So you no longer need to write routing rules every time. Also, regarding the Redis lock, which is part of distributed locking, it's also implemented as a template. Then cross-service calls are also a frequent operation. Previously, after a REST client call, we had to check if it was null and then determine the status. then check if data is null, and then retrieve the data. This can also be encapsulated easily. After packaging, treat the rest can lie you want to deduct as a parameter. Pass it to the OpenAPI Kana inbook, which is also packaged to determine whether it is a root, check the status, and verify if there is data to retrieve. This packaging helps streamline the code significantly. Although it's a small detail, the streamlining effect is excellent. Now let's introduce the security architecture part, where we used to handle JWT. If compatibility requires kicking users offline, this can be addressed. Between microservices, many interfaces need to be open to synchronize blacklists with each other. I don't think that's a very good solution. I believe my approach can be recommended to everyone. My solution is to write a filter in Redis after issuing the JWT, and then from there, when a request is received, the gateway checks Redis to see if the filter exists. If it exists, allow it to pass through to the internal system. Internally, identity is still verified through JWT, so as long as you revoke the corresponding entry in Redis, you can immediately force a user offline. For the offline feature, you don't need to do much or open interfaces for each service to synchronize blacklists. Finally, let's talk about the project structure. It's a Kubernetes cluster, and each project is within the service. It's a monorepository, meaning all projects are in a single repository. This setup has several advantages. The first benefit is that AI can simultaneously understand your code and the context of your K8s deployment configurations. The second advantage, which I've mentioned in other videos, is local K8s containerized development. This way, you can skip the process of setting up Docker Compose. You no longer need to go through the hassle that used to happen after finishing experiments while developing a service. Previously, you had to migrate scripts, configurations, and network architecture from Docker Compose to K8s, but now you can avoid all that. Another advantage is that I've moved the gateway and authentication services into the SDK. That is, for all your projects, you may have many, not just one or two, but potentially a lot of them. All your gateway and authentication services can directly reference this SDK, which automatically provides all the gateway and authentication service functionalities, including login, logout interfaces, and token refresh interfaces. So for these two services, most tasks don't need to be done. You only need to configure the gateway routes and implement specific logic for authentication services, such as permissions and unique third-party validation logic, while basic login, logout, and token issuance are handled by the SDK. These are already set up in the SDK. Moreover, login services and Exchange Gateway for all your projects are managed uniformly, significantly reducing your management costs. Lastly, let's take a look at the SDLC section. Even though it's the most basic part, every element is still very important. In observability and monitoring, the logging part has switched to fully asynchronous high-performance logging, utilizing ring buffer and OS asynchronous writing to maximize logging efficiency. Daily logs carry a trace ID, facilitating the positioning of the final context and full link tracing. Automated context is also provided, automatically attaching a trace ID from interfaces to OpenFeign client calls and Kafka producer messaging. If an exception occurs, the trace ID will be returned to the user along with the exception, making it easy for users to report issues with the trace ID for precise problem localization. Metric governance has been unified, which is mentioned in other videos and the monitoring video, so I won't elaborate here. Efficient optimization has also been done on metrics, and deep integration has been carried out for the Slater pool. System governance includes standardized startup procedures. This part involves template master mode, template code. Then all the services just need to use this, implement this, extend this class, and implement this method. Then you can focus on writing their customized startup program. Then, like every service at the beginning of startup, there will be a cache loading process. He has also prepared the cache loading template. All the logs of cache loading have been prepared. He just needs to implement the specific code for key level loading. The other parts, such as threading and logging, the templates have already been made. So this is the standardization of system startup. Then there's data consistency and security. For the entire system's JSON processing, it is uniformly using JSON, including that. Interfaces, Redis or Kafka, serialization, all use Jackson, unlike others who, without planning or standardization, some people use. Faster JSON, some are like Jackson, and the configurations are all different, causing many discrepancies in serialization and deserialization of the entire data. Then the data of the entire system at the base level will have many inconsistent issues. At the same time, Jackson's configuration actually has many details. There are some security details, performance details, and serialization rules for time, null, and scientific notation details. All of these are standardized. Another part is data consistency in auditing. In many of my previous companies, when doing data auditing, manually write out which fields, which words have changed. After manually writing those things, then write them into a table. My approach was to write an object specifically designed to handle these kinds of differences. You just need to throw the pre-change object and the post-change object into it. It will automatically return a JSON telling you which fields have changed. Then uniformly write this JSON into the table, and that's it. In this way, whether checking account changes or position changes, it should be handled uniformly between services. Then the entire auditing process is standardized and unified. Then lastly, there's the testing part. Before, when we tested DB, we would use some in-memory databases. I have integrated a containerized test here, containerizing MySQL, Redis, and Kafka. This has several benefits. The first benefit is that all these tests are containerized, processed in memory, so you don't need to build an external dependency. Yes, the testing execution efficiency will be much faster. The second advantage is that you don't need to mock anymore, because with mock, you can't test database version differences. All my tests pull real Docker images. They're all real fixed versions. So you can test the version differences of various databases. It can test this. Okay, and finally, in this project, there are recommended configurations provided for both the V1N setup and Maven. And in addition to the basic Maven, optimized configurations for AVAV&D are also provided. This can be used in compilation, local development compilation, and CI/CD compilation, all using this configuration.